Hello students, in this video we are going to learn about total internal reflection. Let's see. Also known as TIR, the short form for total internal reflection. Here we will again take two different kinds of optical medium. One is rarer medium, the other one is optically denser medium. Let's say XY is the interface to rarer medium and denser medium. Above XY everything is rarer, below XY everything is denser medium. Let's draw normal to the interface. In order to experience total internal reflection, it's mandatory that ray of light must incident from denser to rarer. This condition is very much important. I am repeating, here it's mandatory that ray of light must incident from denser medium to rarer medium. According to law of refraction, if a ray incident from denser to rarer, the ray would bend away from the normal. Let's take this as R1, let's take this as I1. It's apparent that I1 is less than R1 because it's bending away from the normal. Now if I increase the angle of incidence, let's take this angle as I2, again the refracted beam will increase its refracting angle. Now still if you increase with some other angle by bit magnitude, it will still go away from the normal. Let's call this as R3. So as you go on increasing the incidence angle, the refracting angle is also increasing. But now pay attention, at a particular incidence, let's call this as I4, the refracting beam may go this direction. Then the angle over here is 90, which is equals to R4, R3 and then R4. Corresponding incidence angle is I4. This is very much important. Here we will call I4, particularly I am going to call it as equals to IC. Why IC? C stands for critical. So IC is known as critical incidence. Why this is called particularly critical incidence angle? Because the refracting beam is making an angle 90. Then what is much importance of this critical angle over here? If any ray incidence above critical angle, let us say this direction, let's call this as I5, the ray would give me total internal reflection, TIR. Why it is called TIR? The 100% of incidence beam will get reflected in the same medium. That's the reason it is called TIR. Pay attention, it's reflection, not refraction. Why it is not refraction? Because ray of light is not entering into the other medium called denser to rarer. Still the ray here is in the same medium, that is called in the denser medium, only the direction got changed. The propagation of the ray direction got changed, but still in the same medium. Now if you apply Snell's law for particular case, for IC, what we would get, ray incident from denser medium. So we starts from denser medium. Apply Snell's law for IC. Then what we are going to get, the denser medium is having refractive index N2, sine of the angle is IC is equals to, the rarer medium is having refractive index N1 and sine of the angle over there it is R, but this is equals to 90. So I will put N2 sine IC is equals to N1 sine 90. I'll take this as R4 for our convenience. We substitute the values. Here we can write sine IC is equals to, sine 90 is 1. So this would give me N1 upon N2. If at all you are interested to calculate what would be the IC for a pair of refractive indices, we can take it as IC is equals to sine inverse of N1 upon N2. Again, if the refractive index which we have taken earlier is air, then the refractive index N1 is equals to 1. Then IC will give me as sine inverse of 1 upon N2. This formula is useful to calculate what would be the critical incidence if I have a dense material, optically denser medium of refractive index N2. So if you know N2, you can find out IC. If you know IC, still you can find out the refractive index of the dense material. So this is very much important. Now my question is, what is the use other than this finding the refractive index? We use this principle for optical fibers. You know optical fibers, how they look like. Optical fiber is made up of core at the central part and surrounded by cladding. Let's take this. So this is the core and this is the cladding from here to here, let us say. And dotted line here is indicating the optical axis of the fiber. If any ray incident here within the acceptance angle, we will learn what is acceptance angle. The ray would suffer total internal reflection. This is how the light rays will travel in the optical fibers without any loss of light energy and for larger distances. We are using total internal reflection where it took place 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. The multiple total internal reflections will cause the light to send from one end to another end. So where it is taking place? On the opposite walls of the core of the optical fiber. We'll see in detail in the next lecture what is acceptance angle, what is cone of acceptance angle, what is numerical aperture. The numerical aperture means light gathering capacity of an optical fiber. Thank you very much. In the next lecture also we will see some numericals based on critical angle. Thank you very much.